The first thing you need to realize with this particular tutorial is that it kind of has a little bit of vagueness on account of the fact that you could either use gravitational acceleration as 9,8 meters per second squared downwards or as 10 meters per second squared downwards. And if you had calculated the gradients of the graphs, you would have noticed that it was actually 10, and yet many of you use 9,8. So there is just a little bit of room for error, and it's more the method that counts than the exact number that you get as an answer. So let's start at the beginning. We've got a rubber ball. It's thrown downwards at a speed of 6 meters per second. If it's thrown downwards at a speed of 6 meters per second, let's take a look at that. If I throw something down, it's going to speed up. It's going to start at 6 meters per second and go faster and faster and faster until such time as it hits the ground. It does hit the ground, and then it suddenly stops. And when does that happen? 0,3 seconds after we threw it down. It bounces back upwards. Assume the collision between the ball and the floor is elastic, and ignore the effects of air resistance. If it's an elastic collision, whatever this velocity is over here, I will bounce back with exactly the same. So let's say that's x. I will bounce back up again with exactly the same velocity, but in the opposite direction. So that's our velocity time graph that we can use in order to try and calculate and explain everything. It says take down to be the positive direction. So let's think about whether we have done that. We threw down at 6, so that's down. Gravitational acceleration is 9,8 or 10 meters per second squared downwards, and this is a positive gradient. So I have taken down to be positive throughout this. Calculate the speed with which the ball hits the floor. I have got, go slowly through these, an initial velocity of 6 meters per second down. I have got a time of 0,3 seconds that it was in the air. I've got an acceleration of positive, because it's 9,8 and down is positive, meters per second squared. And the question that they're asking me is the final velocity. So I can take an equation of motion. I can go V is equal to U plus AT. 6 plus 9,8 times by 0,3, and I land up with 8,94. It's a positive answer, so it is meters per second, and it is also down. So that value at the point where it hits the ground is 8,94, meaning that this must be in the opposite direction after the bounce, 8,94 meters per second. This is a velocity time graph. Time is in seconds, velocity is in meters per second. Right. Question 2. Calculate the height from which the ball was thrown. So I need to now say how high was it before it landed up hitting the ground. I can use a whole lot of different information. I may be able to use this velocity as a final velocity, but I'm going to try and just use this information and get a calculation of a displacement. Displacement is ut plus a half at squared. My starting velocity was 6, the time was 0,3 plus a half, 9,8. All of these are positive because they're all down, 0,3 squared. And that becomes 2,24 meters. So that was 2,24 meters above the ground before it hit the ground. That's this portion of the motion. Calculate the maximum height to which the ball will bounce. What information have I got? My initial velocity is 8,94 meters per second up. So that's going to be negative. My gravitational acceleration is still 9,8 meters per second squared down. I know that at the top of its projectile, all the way at the top, its final velocity is 0. So this would go all the way until it hits the 0 line. And the question is, what is the height? I can say v squared equals u squared plus 2as. And I will land up with 0 squared is equal to negative 8,94, because that was up, squared, plus 2 positive 9,8, and a distance. And my distance turns out to be negative 4,08 meters, which really means 4,08 meters upwards. You are expected to interpret these signs into a word at the end. 2.4, calculate the time it takes the ball to reach that maximum height from the time that it was thrown. I'm going to work out the time for just this portion of the journey. Then I'm going to add 0,3 onto it and see what I get. So, I can say v is equal to u plus at. My u is 8,94 meters per second up, so that's a negative 8,94, plus positive 9,8. Time is, I do not know, but I do know that at the end of that I have got a velocity of 0. Calculate the time, it turns out to be 0,91 seconds. So my total time is 0,91 plus 0,3 plus 1,21, sorry, not plus, equals 1,21 seconds. That's the total time that it was in the air up until it got to the top of its projectile. Just to remind you what this picture looks like, what I've done is I'm a monkey, I'm in a tree. It turns out I am 2,24 meters in the air. The ball gets thrown downwards, and then from the ground it bounces upwards again. So that turns out it bounces a bit higher than it came down from. So that is the journey that you're going to actually go on. The next thing that they ask me is to draw a position time graph, a velocity time graph. Good news, I've already got a velocity time graph here. So that was how I drew the velocity time graph. On these axes, by the way, I must add something here. I better put my total time 1,21 second. It's the time, so it's in seconds already. Sorry, this is not writing beautifully. 1,21. Okay. Over there, and 0,3 over there, and all my other data is there. What about a displacement time graph? It doesn't say what I need to use as my reference point. I am going to use the place where it was thrown from as my reference point. This is a displacement time graph if I use the ground as the reference point. So I started up in the air, it speeded up, so the gradient increases, it then hits the ground and slows down all the way up to the top of its journey over here. That means that 0 is the ground. And it wants to know how high I was in the air. 2,24 meters is where I started. By the end of this journey, I have gone how high up in the air? 4,08 meters. That's not looking terrific. Let's try. Just get that a bit clearer. So there we have a slightly neater version of the graph coming down and bouncing up again. Over here is the ground displacement at 0. I've used the information that it was launched from 2,24 meters above the ground, and when it bounced again it went up to 4,08 meters above the ground. The next one asks you for acceleration time. Acceleration, and remember they said upwards has to be, downwards is positive, so acceleration is downwards, so it's 9,8. Acceleration is in meters per second squared. and it stays constant through the entire journey of the thing. Well, not 100%. Actually, in the bounce, you get this split second where it comes down at 0,3 and then is exactly the same again. And then, so it kind of, but this was an invisible bounce. There we go. Something like that.